In this episode, we're going to build a calm, practical way to think through one of the most confusing feelings in Linux. The system insisting a disk is full when, to your eyes, it clearly is not. New learners often picture storage as a single bucket that fills up with bytes, and when the bucket is not full, everything should still work. Linux storage is a little more layered than that, and those layers matter because different limits can be hit first. When you learn to separate capacity from inodes, and you learn a simple mental checklist for investigating, you stop guessing and you start diagnosing. This topic also shows up on the exam because it tests whether you understand what a file system is actually responsible for, not just whether you can recognize a scary message. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good place to start is making sure the words you use in your head match what Linux is tracking. Capacity is the amount of data, measured in bytes, that a file system can hold. When you copy a video, download a big file, or store a database, you are consuming capacity. An inode is different, and it is easier to understand if you think of it as a record that describes a file rather than the file's contents. That record stores the file's metadata, like ownership, permissions, timestamps, and pointers to where the data blocks live. Most regular files consume one inode each, and most directories also consume an inode, because directories are also file system objects. The key idea is that a file system can run out of capacity or run out of inodes, and either one can stop you from creating new files even if the other resource looks fine. Once you accept that there are two separate resources, the confusing error messages start to make more sense. When a program tries to create a new file, Linux needs two things: free space for the content and a free inode to represent the file. If either requirement cannot be met, the creation fails, and many tools will report an error that sounds like there is no space left. That message can be literally true for bytes, but it can also be functionally true when there are no inodes left, because from the application's point of view it cannot proceed. This is why you can look at a system that seems to have gigabytes free and still be blocked from saving logs, creating temp files, or installing packages. The system is not lying. It is just telling you that some resource needed to create a file is exhausted. The inode problem is especially common on file systems that contain huge numbers of tiny files. Imagine a mail server that stores each message as a separate file, or a web cache that creates thousands of little objects, or a build system that generates many small artifacts. Each file might be only a few kilobytes, so capacity barely moves, but inode usage climbs quickly. The opposite situation can happen too, where you have plenty of inodes left but capacity is drained by a handful of large files. What makes this tricky for beginners is that they often check only one thing, usually free bytes, and then they feel stuck when the symptoms do not match. The mental shift is to remember that a file system is like a library with two limits: shelf space for pages and an index card for each item. If you run out of index cards, you cannot add another book even if shelves are empty. Now let's build the mental checklist promised in the title, because the real skill is not memorizing a definition. The first step is to confirm what storage location is actually failing, because not all paths live on the same file system. A system can have multiple mounted file systems, and one small file system can fill up even when the main disk has space. For example, temporary directories, home directories, or application data directories might be separate mount points. When you see a failure, anchor your thinking to the specific directory involved and assume it might have different limits than you expect. It is common to mentally think of the machine as one disk, but Linux often treats storage as a set of separate containers. That means the first question is not how much space does the computer have, but rather which file system holds the path that is failing. The second step is to check capacity versus inodes as separate questions, because that is the heart of this topic. Capacity answers whether there are free data blocks left to store content, while inode availability answers whether new file system objects can be created. The outcome is what matters. If the system cannot create a new file, both resources must be considered. When capacity is low, you tend to see failures with large writes first, and you might still be able to create tiny files for a while. When inodes are low, you tend to see failures even for empty files or small config changes, and the system can feel mysteriously fragile. Logs may stop updating, services may not start because they cannot write a PID file, and package managers may fail because they cannot create temporary files. This pattern recognition is part of the checklist because it guides you toward the right limit without guesswork. The third step is to look for the reason a file system is consuming space or inodes faster than expected, and beginners should focus on the usual suspects before they chase rare edge cases. A classic culprit is log growth, especially if a service is stuck in a loop that produces repetitive messages. Another common cause is a runaway temporary directory, where an application creates many small files but fails to clean them up. Cache directories can also grow quickly because caches are designed to trade storage for performance. For inode exhaustion specifically, the directory trees that hold many small files are the places to suspect first, such as mail spools, caches, container layers, and application runtime directories. The goal is to identify not just that a limit is hit, but what kind of content is causing it. The fourth step is to remember that deleting files does not always immediately restore what you think it should restore. This sounds odd at first, but it is a common reason people feel like a disk is full even after they remove data. In Linux, if a process has a file open and you delete the file, the directory entry is removed, but the data can remain allocated until the process closes it. From the user's perspective, the file is gone, but from the file system's perspective, space may still be tied up because something is still using it. This is one of those Linux ideas that is deeply logical once you learn it. The system cannot discard data that a running process might still need. So part of your checklist is to consider whether a running service is holding onto deleted content, which can happen with log files, temp files, or rotated files. The fifth step is to consider reserved space and special file system behaviors that can make capacity look misleading. Some file systems reserve a portion of space for administrative use so that the system can keep operating even when a normal user would otherwise fill the disk completely. This protects the machine from a total meltdown because critical services still need to write small files and logs. The result is that a non-privileged user might see write failures even though there appears to be some free space. The system is effectively saying that the remaining space is not available to you under normal conditions. The exam likes this concept because it tests whether you understand that free space is not always the same as usable space for every user. In your mental checklist, that means you consider who is trying to write and whether privilege level changes what space is available. The sixth step is to think about mount options and read-only situations, because a disk can behave like it is full when the real issue is that the file system is refusing writes. File systems can become read-only after errors as a safety mechanism, and storage can also be mounted intentionally as read-only for protection. In that state, applications can produce errors that look like storage failure because the write cannot be completed. This is particularly confusing for beginners because they mentally map any inability to write to a lack of space. Your checklist should therefore include the question of whether the file system is writable right now, and whether the system recently experienced an error that would cause protective behavior. The point is not to memorize a list of flags, but to remember that write failures can come from policy decisions as well as resource exhaustion. The seventh step is to separate local file system limits from broader storage realities, because not all storage behaves like a local disk. Network storage, virtual disks, and layered storage systems can report free space in ways that are not as straightforward as a single physical drive. A remote share might have quotas, or a storage backend might have its own limits that are enforced separately from what your machine reports. Even on a local machine, user quotas can create a similar effect, where the file system has space, but a particular user is not allowed to consume more. The exam often frames this as a troubleshooting mindset. You do not want to assume the number you see is the whole truth until you consider who is writing and what policy might apply. In your checklist, this becomes a quick mental check for quotas and shared storage behaviors when symptoms do not line up. The eighth step is to understand why inode availability is decided ahead of time and why that matters. Many file systems allocate inode structures based on design choices made when the file system is created, which is why an inode shortage can happen even on a large disk. The file system designer is balancing overhead and expected usage patterns, trying to avoid wasting space on metadata that might never be used. If you choose a configuration intended for large media files, but you actually store millions of tiny files, you can hit the inode ceiling earlier than you expect. For beginners, the practical takeaway is that inode limits are not automatically scaled up on demand in every file system, so you must treat them as a real capacity planning factor. On the exam, the concept shows up because it explains why the inode problem is not rare or magical, but a predictable consequence of how a file system is structured. The ninth step is to build intuition about how the system behaves when it cannot create new files, because the consequences can be broader than you expect. Many parts of Linux assume they can write small bits of state, like lock files, PID files, cache entries, and log updates. When file creation fails, services can crash, restarts can fail, and scheduled jobs can silently stop doing useful work. The system might still be running, and interactive commands might still work, but things that depend on writing state can become unreliable. This is why it is so important to treat storage errors as a stability issue, not just an inconvenience. In the mental checklist, you should include a moment where you think about what critical functions rely on file creation, so you can anticipate secondary symptoms and avoid making the situation worse. The 10th step is to avoid a common misconception that free space shown by one tool automatically reflects what every program can use. Different views of storage can be based on different layers, such as the file system, the logical volume, or the underlying device. Even within the file system, there can be differences between what is free in theory and what is free for a particular user under a particular policy. Beginners sometimes chase ghosts because they compare numbers from different contexts and assume one of them must be wrong. The better habit is to treat storage numbers as context-dependent and focus on consistency within the same context. If the path that is failing lives on a specific file system, that file system's limits are the ones that matter first. Your checklist should steer you back to that anchor point whenever you feel pulled into conflicting numbers. The 11th step is to connect this topic to everyday Linux behaviors you will see again and again, because it is not just a one-off troubleshooting trick. Package installations can fail if temporary directories cannot accept new files, even if the package content is not very large. Updates can fail if logs cannot be written or if state cannot be stored. User logins can fail if home directory operations cannot create files, and desktop environments can behave strangely if cache and config writes fail. When you recognize that these failures can originate from a node exhaustion or capacity exhaustion on a specific mount point, you stop treating them as mysterious application bugs. Instead, you treat them as symptoms of a storage subsystem that has hit a limit. The exam tests this kind of reasoning because it indicates you understand the operating system as an integrated set of components, not a pile of unrelated commands. The 12th step is to turn the checklist into a simple mental flow you can replay under pressure without memorizing exact commands or procedures. First, identify the path that is failing and mentally map it to a file system, because the failing location might not be the one you assume. Second, ask whether the failure looks like capacity exhaustion or inode exhaustion by thinking about the kind of writes that fail and whether even tiny files are blocked. Third, suspect the usual culprits like logs, caches, temp files, and runaway file creation, because those patterns explain most real incidents. Fourth, remember the special cases where deleting does not immediately free space, where reserved space changes what is usable, and where read-only behavior or quotas can mimic a full disk. This flow is short enough to remember, but rich enough to prevent you from making the common beginner mistake of checking only one number and giving up. By the end of this topic, you should feel like you have a stable explanation for something that used to feel like a contradiction. A disk can be full in the byte sense, full in the inode sense, or effectively full for a specific user because of reserved space or quotas, and those are not edge cases in Linux. They are normal design outcomes. When you approach the problem with a checklist, you are less likely to panic, and you are more likely to ask the right questions in the right order. The deeper lesson is that Linux is very consistent once you understand what resource is being consumed and what rule is being enforced. Capacity and inodes are two different currencies, and a file system needs both to create and manage files reliably. If you can hold that idea in your head, You will recognize storage-related failure modes faster, and you will answer exam questions with more confidence because your reasoning will be grounded in how the system actually works.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.